I welcome you to Marim Education Services, and we are going to continue from where we stopped regarding reactions of benzene. This video is suitable for students in Senior 5 and Senior 6 who are offering chemistry as part of their subject combinations. If you do not fall under those mentioned category, there are many videos that have been designed to suit your level. Kindly explore the channel carefully. You will find information that suits your level. So we stopped on reaction 5. So here we are looking at reaction of benzene with acid anhydrides. A reaction of benzene with acid anhydrides. This reaction is similar to Friedel-Crafts acylation. It is also slightly similar to Friedel-Crafts alkylation. It is also slightly similar to halogenation of benzene. So here basically we look at the reaction where benzene reacts with acid anhydrides. Still it occurs in presence of halogen carriers, and the products that are formed are known as phenyl ketones. So the halogen carriers, they serve purposes that have been described repeatedly in the previous videos. And if you are watching this video for the first time, I'll refer you to the previous videos on reactions of benzene where we have seen the roles which are played by the Lewis acid catalyst in the reaction mechanisms of Friedel-Crafts alkylation, Friedel-Crafts acylation, and halogenation of benzene. So here I take an example. So we have benzene reacting with this compound. The name of this compound is called, its name is ethanoic anhydride. Ethanoic anhydride, that is its name. So acid anhydrides are compounds that are made up of this functional group. They have this group as their functional group. So any compound that has this as the functional group is what we call as an acid anhydride. Yeah. So for them, they belong to that homologous series. In this case, we outline the reaction mechanism. So I'll bring my benzene. As described earlier on, benzene undergoes electrophilic substitution reactions. So this is how I'm going to write my acid anhydride. We have this compound and there are two of them. We have a bracket implying that this thing is repeated. It is repeated 2 times. So we have CH3. C, this is C carries oxygen, CO, CO. Then this is C, there are 2 of them, but both CH3CO are attached to that oxygen. So this is one CH3CO, then I put oxygen there. Then another CH3CO is attached to this oxygen, like this. Then I also have my Lewis acid catalyst. So we have described previously the roles which are played by this Lewis acid catalyst. If you recall the structures of acyl compounds, for example, if I replace this with chlorine, if I replace this thing here with chlorine, then I come up with the ethanoyl chloride. This part here, if I replace it with chlorine, I come up with ethanoyl chloride. So still, this aluminium is electron deficient, and this part here is first of all, we have oxygen here, which is more electronegative than carbon. So it can take electrons towards itself, but then bring those electrons, donate them to electron deficient aluminium. So once they are donated to electron deficient aluminium, this acquires a partial positive charge. This also acquires a partial negative charge, implying that this is electron deficient, the carbon. Then benzene donates to that carbon. So what do we form in this case? In this case, we shall have the following. We have a benzene ring. This bond here has been broken. As we have seen previously, we shall have here CO, CH3. This group here is attached to one of the carbon atoms. If it goes up, we shall have a plus here. The reason as why this group can either go up or down, simply because those two carbons have the same number of hydrogen atoms. So if I put it up, this one will be electron deficient. Then I also form this compound here, this compound and the halogen carrier. We shall have we have plus Al, Cl3, CH3, like that. That's what I have. Then I expose one hydrogen here. I expose one hydrogen so that I use it to donate electrons, so that electron deficient carbon. Then I lose a proton minus hydrogen ion, so that I form phenyl ethanol. Phenyl ethanol. Then the hydrogen ion that has been lost combines with the other negatively charged species. So that will form, this is what we form. So it donates electrons to, since it is negatively charged, it donates electrons to the hydrogen ion. So that will form ethanoic acid plus our Lewis acid catalyst. So if I complete the equation, I have my product, this, plus ethanoic acid. And that is the first example. I believe one example is enough on that. You are going to try out these questions, because this mechanism of reaction of benzene with acid anhydrides, if you look at it carefully, if you study it carefully, you realize that it is almost similar to that of Fendelkraft's alkylation, Fendelkraft's acylation, halogenation of benzene. For that case, I do not need to work out several examples. You work out those questions. Our next reaction is nitration of benzene. Nitration of benzene, basically here we look at reaction of benzene with the concentrated nitric acid, how benzene reacts with concentrated nitric acid. So the reaction with concentrated nitric acid occurs at 55 degrees centigrade, and it requires presence of a catalytic protonator. It requires presence of a catalytic protonator, and in that case, for this case, the catalytic protonator is concentrated sulfuric acid. So benzene reacts with concentrated nitric acid in presence of a catalyst, concentrated sulfuric acid, at 55 degrees centigrade to form what we call nitrobenzene. And nitrobenzene is yellow in color. So the purpose of sulfuric acid in this case serves to protonate. It donates a proton to nitric acid, and that causes formation of an electron deficient nitronium ion. Remember from our previous discussions, benzene reacts with things that are electron deficient. So what induces formation of an electron deficient species in this case is concentrated sulfuric acid. It reacts with the nitric acid, it protonates nitric acid, resulting in formation of an electron deficient nitronium ion, which will in turn combine with benzene, as we are going to see in this following example. So there are two ways of outlining the mechanism to this reaction. So I'm going to first work out in this first example, we are going to see the first approach. Then in the second example, you will see the second approach. So concentrated sulfuric acid will break it down. You break it down to form hydrogen ion and the hydrogen sulfate ion, like that. Then I write my nitric acid. I'm going to write my nitric acid as HONO2, like that. I write it in that case. I want to form a nitronium ion, yes. And if you studied structure and bonding, we can write nitric acid in that form, yeah. So there are lone pairs of electrons on this oxygen, and those lone pairs of electrons can be donated to electron deficient hydrogen. From sulfuric acid, this proton is electron deficient, so we can take lone pairs of electrons from this oxygen, donate them to hydrogen. As a result, we shall have the following. We shall form, so this is added to this hydrogen so that you have H2O plus, because that oxygen has donated, so it is electron deficient, then NO2, like that. Water, this oxygen, this thing, the water molecule is electron deficient because this oxygen has a plus, it donated electrons. So we can donate electrons to it using those in that bond. As a result, what do we form? We form H2O, a water molecule has been lost, then plus a nitronium ion, which is electron deficient, NO2 plus, because electrons have been taken to this oxygen and nitrogen contributed part of those electrons, so they have been taken away, so it is also electron deficient. So I have now my electrophile. Benzene will then combine with that electrophile in electrophilic substitution reaction. So we donate electrons to it. As a result, we shall have the following. So this bond has been broken. It goes up, then that carbon will be electron deficient. Then I expose this hydrogen here because I want to use it to donate electrons to electron deficient carbon. Therefore, the hydrogen is lost, minus hydrogen ion. Then I form the following. That's what I form. Then this hydrogen ion that has been lost can combine with hydrogen sulfate ion. This one that has been lost can combine with this hydrogen sulfate which was left in step 1 to form, obtain back our sulfuric acid, like that. So this is a reversible arrow. So implying that sulfuric acid is formed back, it did not participate directly in the reaction, it was serving a certain purpose. That is catalytic protonator. So my products, I have nitrobenzene. This is what we call nitrobenzene. Benzene with the nitro group. Nitrobenzene plus water. Plus this water molecule. So that is the first example. So in the first example, we have seen the preliminary stages where concentrated sulfuric acid first breaks down to form a proton, which is added to nitric acid. However, all those preliminary steps can be summarized in the following step. I can simply write concentrated nitric acid plus concentrated sulfuric acid, they form nitronium ion, water molecule, hydrogen sulfate ion. Which other one? Hydrogen sulfate ion. Let me see whether it balances. These are three hydrogens. This is one, 2, 3. Hydrogens are balancing. Nitrogen 1, nitrogen 1. Oxygen, there are 7. 1, 2, 3. 7. I think it balances. Yeah. So we can summarize those preliminary steps in one. I can summarize them in one equation. Then I bring my benzene. In this case, it is substituted benzene. Benzene with a methyl group. The mechanism will almost remain the same. So I bring also my nitronium ion. We get electrons from one of the double bonds, donate them to nitronium group. Then we form the following. So Markovnikov says that this incoming group goes to the nearest carbon with more hydrogens. The carbon here lacks hydrogen for reasons which I've been explaining in the previous examples, but this has hydrogen. So the nitronium group is going to come here. So if it goes there, the one up will be electron deficient. Then we expose the hydrogen here so that it donates electrons to that electron deficient carbon. As a result, we shall lose a proton minus hydrogen ion. Lose a proton. Then we form the following. That's what we form. Then the hydrogen ion can combine with the hydrogen sulfate so that sulfuric acid is obtained back, implying that it is not unchanged. It is not changed, it is unchanged. It was having a certain purpose. It did not participate directly in the reaction. Therefore, my products, I have the following. CH3 NO2 plus H2O. Yeah, that's what I have. So you are going to try out this question on nitration of benzene. Our next reaction is sulfonation of benzene, and basically here we look at the reaction of benzene with concentrated sulfuric acid, how benzene reacts with concentrated sulfuric acid. In particular, it reacts with concentrated sulfuric acid on heating or fuming sulfuric acid at room temperature to form benzene sulfonic acid. So concentrated sulfuric acid in this case, concentrated sulfuric acid, if it has been warmed or if it is in a fuming state, if you've ever opened a bottle of concentrated sulfuric acid, you will realize that there are fumes that come off from that bottle, and those fumes are fumes of sulfur trioxide. So concentrated sulfuric acid or fuming sulfuric acid is in equilibrium with sulfur trioxide gas, and sulfur trioxide is the one that will combine with the benzene, because within it we are going to see that the sulfur atom is electron deficient, as illustrated in this example. So we have this example. In some books they specify this heating to a certain temperature, which is okay. You can they specify. If you encounter that in previous literature, don't feel offended. It is also fine. I can as well put fuming sulfuric acid on top there up without heating. It is also very fine. So for concentrated sulfuric acid, as I have explained earlier on, this acid is in equilibrium with sulfur trioxide. It is in equilibrium with fumes of sulfur trioxide. So it has sulfur trioxide. Then it also has hydrogen ions or hydroxonium ions and the hydrogen sulfate, like that. Then the benzene combines with the sulfur trioxide. So I'm going to write my sulfur trioxide in this form. Like that. So these bonds here, the double bonds are polar. So I use one of them, one of the three. For example, if I use this, it is polar because oxygen is more electronegative than sulfur. So it acquires a partial negative charge. Then this has a partial positive charge, indicating that it is electron deficient. So benzene donates to it, like that. So we shall have the following. We have our ring, then a bond there, the bond there. Then SO3, a sulfur atom that carries 3 oxygen atoms, but 1 oxygen has taken electrons towards itself. So there is a negative charge there on that, implying that 1 oxygen has a negative charge. Then this will be electron deficient. So we expose the hydrogen here. We use it to donate electrons to that electron deficient carbon. As a result, we shall obtain the following. We shall obtain plus hydrogen ion that has been lost. So this hydrogen ion can shift there up. It can shift there up because this is electron rich. Electron rich. So we can have a proton shift. So that we obtain benzene sulfuric acid, like that. So that is what we call benzene sulfuric acid. I complete my equation here. The product is benzene sulfuric acid, like that. Yeah. I leave this question. Try out that question. Yeah. As of now, allow me stop here.